Adjacency matrix, a 2D matrix, can be used to store a graph. A graph G, V, E, where V is 0, 1 to n minus 1, can be represented using a 2D matrix, a integer array of size n into n. So, int adjacency matrix 2020 can store a graph with 20 vertices. Int ij, so 1 indicates that there is a presence of an edge and 0 indicates the absence of an edge. A graph is represented using a square matrix. Adjacency matrix of an undirected graph is always symmetric, that is aij is equal to abi. Adjacency matrix of a directed graph is not symmetric, that means aij will be equal to 1, indicating that there is a directed edge from vi to vja. So there is vi to vj, there is a directed edge and it is not a symmetric adjacent matrix. So this is a undirected graph. Undirected graph is symmetric, that means 0 0 is 0, 0 1, 0 1 is 1 and 1 0, 1 0 will also be 1, so it is symmetric. Similarly 2 3, 2 3 is 1 and 3 2 is also 1. This is the directed graph. Directed graph is unsymmetric. Zero one is 1, but 1 0 is not 1. It is 0 because it is directed from 0 to 1 and not the reverse. Adjacency matrix of a weight graph. For a weight graph, the matrix ADG is represented as, if there is a edge between I and j, then ADG ij is equal to the weight of the edge, otherwise it is 0. So the example 0 to 1, there is a weight 2, so from 0 to 1 we will write 2. 0 to 2, there is a weight 3, so 0 to 2, 3. But 0 to 3, there is no edge, so ADG ij will be equal to 0. This is how the table is completed. Adjacency matrix of a graph is very simple to implement. Adjacency matrix representation of a graph wastes a lot of memory space. Such matrices are found to be sparse. They waste a lot of memory space. Above representation requires space n square elements for a graph within n vertices. If the graph has e number of edges, then n square minus e elements in the matrix will be 0. Presence of an edge between the two vertices can be checked in a constant timer. So presence of the edge between the two vertices can be checked in the constant time. If ADG ij is 1, that means an edge is present. If it is 0, it means an edge is absent. The degree of the vertex can be easily counted by calculating all the non-zero entries in the corresponding row of the adjacency matrix. Adjacency list. A graph can be represented using a linked list. For each vertex, a list of the adjacent vertices is maintained using a linked list. It creates a separate list for each vertex vi in the graph G, V, I. So this is the adjacency list. In the adjacency list, 0 is adjacent to 1, adjacent to 2, adjacent to 3, adjacent to 4. So 0, 1, 2, 3, 4. 1 is adjacent to 0 and 1 is adjacent to 3. 1 is adjacent to 0, 1 is adjacent to 3. So 0 and 3. Then 2 is adjacent to 0, 2 is adjacent to 3, 2 is adjacent to 4. 0, 3 and 4. 3 is adjacent to 0, 1, 2 and 4. 4 is adjacent to 0, 2 and list of the graph with n nodes can be represented by an array of pointers. Each pointer points to the linked list of the corresponding vertex. Adjacency list representation of the graph is memory efficient, unlike the adjacency matrix, which wastes a lot of memory when the graph has a large number of vertices but a few edges. For an undirected graph with n vertices and e edges, total number of nodes will be n plus 2e. If e is large, then due to overhead of maintaining the pointers, adjacency list representation does not remain cost effective over adjacency matrix. Degree of a node in an undirected graph is given by the length of the list. So length of the list gives the degree of the node in undirected graph. Checking the existence of an edge between the two vertices I and j is also time consuming. For adjacency matrix, it was not time consuming, it was time efficient, because we just had to check whether ADG of I and j is equal to 1 or not. If it is equal to 1, then you have an edge. If it not equal to 1, then you do not have an edge. But this procedure is time consuming for adjacency list. For adjacency list, the wastage is not there of memory. For adjacency matrix, there is a lot of memory wastage.